Here are some basic properties of rotation matrices. Okay. The first one, well, first of all, recall that they are 3 by 3 matrices in 3D. And let's call them R. Or more generally, if they are taking you from frame 0 to 1, let's call them frame, R 0 to 1 like that, as we did. That's the notation. Well, the first property is that the determinant of any of these rotation matrices, or let's say, equals 1. The second property, which perhaps is the most important property, and the first property is sort of a special case of this, is that R 0 to 1 inverse equals R 0 to 1 transpose. Okay. Another way of saying that is that if you have a rotation matrix R 0 to 1, and then you multiply that with R 0 to 1 inverse, that of course equals identity by definition of inverse. And the inverse exists because the determinant is not equal to 0. But because we've said that the inverse is a transpose, this equation is true. So, i.e., for any rotation matrix R transpose equals identity. These two things, of course, mean that these matrices are what are called proper orthogonal matrices. Are the same as rotation matrices in 3D. Orthogonal matrices means that R transpose equals I. The proper orthogonal matrix means that the determinant is also equal to 1. Okay, so those are rotation matrices. Those are the two main rotation matrix properties. Inverse of R equals transpose of R. Of course, note this is only a property of rotation matrices. This, of course, you know very well, and not 3 by 3 matrices in general. Right. So if you have a general 3 by 3 matrix, computing the inverse, you have to go through a certain process. For instance, involving determinants and minors, or some kind of Gauss elimination process. But for rotation matrices, taking the inverse is as simple as taking the transpose. Okay. So that's those are two main properties. Now, how do you prove this property? Let me leave that as an exercise. Prove property 2, hint. So for general rotation matrix, use the dot product expression for R0 to 1 for a general rotation matrix. So this is something that we did in a previous lecture. We developed a notation involving dot products of vectors in frame 0 and frame 1 for the matrix R0, 1, and you can use that essentially to show that this is equal to true. Okay, so I'll leave that as an exercise. Another property, 3, yeah, so rotations are not commutative. Specifically 3D rotations. I.e., if you have two rotation matrices, so it says need not be two rotation matrices. Or let's just call them R1 and R2, two matrices, then R1, R2 not equal to R2, R1, typically. Except in special cases. Okay, so we can develop that